Have you ever wondered what invisible forces are at play, harnessing the wind's power and converting it into electricity we can use every day? It is truly fascinating how these massive structures capture the kinetic energy of the air. The primary aerodynamic forces acting on wind turbine blades are lift and drag. These are the same fundamental forces that allow airplanes to fly, but in a wind turbine, lift is the useful force that drives the rotation of the rotor, and drag is a secondary force that must be managed. Think of a wind turbine blade as an airfoil, similar in cross-section to an airplane wing. When wind flows over the specially shaped surface of the blade, it travels faster over the curved upper surface and slower along the flatter lower surface. According to Bernoulli's principle, faster-moving fluid exerts less pressure. This pressure difference creates a net force perpendicular to the direction of the airflow, which we call lift. This lift force is what pushes the blade forward, causing the turbine to spin. Meanwhile, drag is the force that opposes the motion of the blade through the air, caused by friction between the air and the blade surface, and by pressure differences as the air is displaced. While some drag is unavoidable, engineers design blades to maximize lift and minimize drag for optimal performance. Understanding and manipulating these forces is crucial for designing efficient wind turbines. Engineers carefully sculpt the blade's profile, known as its airfoil, to optimize the lift-to-drag ratio. They also adjust the blade's pitch, which is its angle relative to the incoming wind, to control the amount of lift generated. This allows the turbine to operate efficiently across a wide range of wind speeds, preventing damage in very high winds and maximizing energy capture in moderate conditions. This active pitch control system is a key element in modern turbine operation. A critical concept in wind turbine aerodynamics is the angle of attack, which is the angle between the relative wind direction and the blade's chord line. The chord line is an imaginary straight line from the leading edge to the trailing edge of the airfoil. Engineers meticulously design the blade to have an optimal angle of attack over most of its length, balancing lift and drag. If the angle of attack becomes too large, the airflow can separate from the blade surface, leading to a condition called a stall, which significantly reduces lift and increases drag. This can negatively impact performance and even structural integrity. By deeply understanding how lift and drag interact with the complex geometry of a wind turbine blade, engineers can continually refine designs. This leads to turbines that are not only more powerful and efficient in generating clean energy but also more durable and reliable. The continuous innovation in blade design, driven by these aerodynamic principles, is essential for advancing the capabilities of sustainable energy systems.